In the previous video, we looked at sine and cosine, and we showed that sine and cosine are two functions that oscillate. We're going to talk about the oscillation behavior of sine specifically, but the same concepts also are seen in cosine as well. We're going to focus on looking at the amplitude, the period, and the frequency. We'll define what these mean, and then we'll talk about ways we can change them. Now, oscillation systems are really important. In engineering and physics, you see them in oscillating pendulums. You see them in spring mass systems. We're going to focus on systems without looking at decay, right? What I mean by that is we're looking at systems that will oscillate back and forth and never go back down to any equilibrium, right? In reality, that always will happen. Spring mass system, if you let it go, it's going to oscillate until some point where it stops oscillating because of friction, because of a whole bunch of other things that we're going to neglect completely. We're going to do that just so we can focus on the concepts of oscillation. And what we're going to talk about is how do we identify what the amplitude, period, and frequency are, and how do we change them by looking at the function and understanding what the function actually is doing. Here we have sine of t. We can call this sine of theta, we can call this sine of x. It doesn't really matter, it just defines your x-axis. You know, from the previous video, we can talk about sine in terms of degrees or radians. In a lot of conventions, if we put a variable like t, we're talking about it in terms of radians. Now, the important thing is what the range of our amplitudes are, right? So I put it in terms of time, and we're going from 0 to 2 pi in this graph. Now, realistically, this goes from negative infinity for t to positive infinity for t. So this goes on forever along the x-axis, but it's constrained in the vertical axis from -1 to +1. And we're going to define a couple things. Here we see one cycle. So the number of cycles tells us the number of times I can have a repeating part. So this one cycle is repeated over and over. So I take this whole segment and I paste it over here and I paste it over here. When I see that repeating segment, that part that is repeated is considered a cycle. So the time, right, if I look at this in terms of a time scale in seconds, the time it takes for one cycle to be complete is considered a period. So period capital T is the time. In this case, it will be 2 pi. The frequency is how many cycles you get in 1 second. So this is just going to be 1 over t. And this is going to have units of hertz. This is going to have units of seconds. And the number of cycles is just unitless, right? So how many. Amplitude is the height. We're going to look at it first from the peak to the trough, right? And then half of that. So peak to baseline, essentially. In this case, it's going to be equal to 1. Now, your amplitude could be any physical parameter. It could be a distance. It could be a angle, right? If you're measuring like the pendulum, what's the angles that it's oscillating between. It could be a voltage if you're measuring voltage that's oscillating. It could be a temperature if you have some kind of system that's cycling. So it could be any physical thing that you can measure or quantify. So there's your amplitude, and here's your period, right? So you define the period as one cycle. Now we can expand this graph, and that's all this is showing. These are the same graphs, but I'm showing more cycles here, right? So we're still going from a -1 to 1 amplitude. So that part's still the same. Here's that first 0 to 2 pi segment that's shown here. And I take that cycle and I repeat it 1, 2, 3, 4 more times. So a total of 5 cycles are shown here. Goes from 0 to 10 pi. If I change the range in the amplitude, so the graph itself is still not changing. We're still going from -1 to +1 for the curve itself. But the range that I'm showing is larger. I'm going from -5 to +5. So the graphs look different just because of that. So keep this in mind when you're presenting data, that you want to keep the range of your graphs consistent, or else you might be telling a completely different story when you don't really intend to. And so again, you can define the period as from the peaks to peak, or you can go from 0 to the second 0 points, because you're going to cross a 0 coming down and then coming back up. That's the period that you're looking at. So either way is fine. So in this case, this graph has an amplitude of 1, a period of 2 pi, and a frequency of 1 over 2 pi hertz. We're going to manipulate this sine of t as our baseline function in different ways to change the amplitude, to change the period and frequency, to shift the graph left or right, and shift the graph in the vertical direction. We'll look at all the different ways to do that, and then at the end of this video, I'll have a sequence of graphs or functions, and see if you can graph based off of the concepts that we're going to be talking about in this video. All right, so the first thing we can vary is the amplitude. So the coefficient in front of the sine t function changes your amplitude. By default, if we just say sine t, we're saying that the amplitude is equal to 1, the coefficient is equal to 1. So here are two other amplitudes, 1/2 and 2. And so we can see what this looks like on our graph. So in green is the amplitude of 1/2, as we can see here. In red is our baseline amplitude of 1, and in blue our amplitude of 2. You can see that the frequency and the period have not changed. You're hitting peaks at the same time, pi over 2. You're hitting 0 points at 0, pi, and 2 pi. So only amplitude is changed and varied by changing your a constant here, or coefficient here. And if we extend it by multiple cycles, going from 0 to 10 pi, we can see what the effects are. It's still non-decay, no frequency change, no amplitude change. So it's still 2 pi for the period and 1 over 2 pi for the frequency. Now we can see what happens when we change the frequency or period. So we're going to keep the amplitude fixed at 1, and we're going to look at omega. Changing omega is going to change my period and my frequency. We define the period as 2 pi over omega. In default case, this was sine t, so default omega is equal to 1. The frequency is going to be 1 over the period, which is the same as the omega over 2 pi. So let's take a look at a couple examples. So we have an omega of 1/2 in green and omega of 2 in blue. So here's my baseline sine t in red. And so this is going to have a period of 2 pi and a frequency of 1 over 2 pi. Next, we'll look at sine of 1/2 t. The period is 2 pi over 1/2, or the period is 4 pi. The frequency is omega over 2 pi, so 1/2 over 2 pi, or 1 over 4 pi. Okay, so the frequency goes down, the period increases. So this is all on, both of these graphs are graphed from the 0 to 4 pi scale, so we can compare them directly, right? So you doubled your period. What do you think sine 2t is going to show, right? So if 1/2 stretches out your graph, sine 2t is going to compress your graph, right? So your frequency goes up. This makes sense because omega now is increased. So from this function, we see that your frequency is going to be 1 over pi hertz. Your period, 2 pi over 2, is just going to be pi. And we can see that showing up here. Again, this is going from 0 to 4 pi. And you see when you stack all of these graphs together, it's even more apparent the effects of omega on the frequency and the period. Remember, frequency and period are tied directly together. The next thing we're going to look at is phase shift. How do we shift the graph in the horizontal direction? We're going to need to keep omega in there because how the period changes will affect what the phase shift effect will also be. And we'll see that in a second. So we looked at how omega influences frequency and period. If we want to shift the graph to the left or right, we can use the phase shift with the coefficient phi. Now phi is dependent on what the period is, so omega has a direct influence. That's why we write this as sine omega times a quantity t minus phi. We're going to first look at this when omega is equal to 1, so we see just the influence of phi. Then we'll look at this when omega is equal to 2, so that we can see the influence of omega on phi. Now, if omega is equal to 1, then this is just like sine t. So the amplitude is going to be 1, t will be 2 pi, the period will be 2 pi, and the frequency 1 over 2 pi hertz. Right? So that's the baseline we're looking at, and all the graphs in this slide are going to be looking at that. And all we're going to do is look at the phase shift. But one thing to recognize, if I write sine t is equal to sine t minus 2 pi, this is true, right? So these two terms are true, are equal to each other because the period is 2 pi. So if I say phi is a phase shift, it's a delay in starting your graph by this phi value. This means that you're phase shifting by 2 pi, by one period. And if we think about it from the perspective of a unit circle goes from 0 all the way to 2 pi and we're back again, right? That's also the definition of the period. So whatever happens at sine t will happen again at t plus or minus 2 pi, again at plus or minus 4 pi, again at plus or minus 6 pi, and so forth. Right? That's a definition of this oscillation and definition of period. So we want to look at the phase shifts from some value between 0 and 2 pi. So we'll look at a couple of them here. So here we show the graph, the baseline graph in red, sine t. Then we have the blue graph, sine t minus pi over 2. So we have a pi over 2 delay. And so that's shown here. So what do we mean by delay? The graph in red starts at t equals 0, and it increases to 1 and then decreases. If we think about this blue graph as a delay of pi over 2, so it's like we're not doing anything for pi over 2, and then we start, right? Obviously, there is something that's going on here, but we talk about this from a delay or phase shift perspective, because if I grab this point here and I shift it back pi over 2, now the blue graph would overlay the red graph, right? So any oscillation with the same amplitude and same frequency or period, you can phase shift them back. You can determine how much these two graphs are phase shift from each other. And you can stack them on top of each other. And this phase shift has a real physical meaning depending on what you're measuring, right? So let's take a look at a couple more examples. Sine t minus pi, we're phase shifted by pi. And you can see that right there, right? So if I grab this point in the green graph and I shift it over by pi, we'll have them stack. And then sine t minus 3 pi over 2, right? So this is going to be shifted by 3 pi over 2. If I grab this point, I shift it over here. Now, interesting thing that we can see from these graphs, if you subtract by a phase shift, you can also add by a different value and shift it in the opposite direction, right? So for this green one, I said if I grab this green point and I shift it to the left by pi, I would get sine of t. It would stack on top. What if I grab this point of the green, right, and shift it to the right by pi? I'll get the same thing. Now, that means that sine t minus pi is equal to sine t plus pi. That makes sense too, because your period is 2 pi. So whether you go in one direction or the other direction by pi, half of that period, is the same thing, because your oscillations are repeating itself forever and ever. So if you go half a period forward or half a period back, it looks the same way. All right, so let's take a look at if omega is equal to 2 instead. All right, so here we have sine 2t as my baseline graph, right? So omega is equal to 2. So if omega is equal to 2, my period now changes to pi and my frequency is 1 over pi. We still have an amplitude of 1. So I graph sine 2t as my baseline function for all these 4 cases here. or all these three cases here. What we see in this middle graph here is that sine 2t is equal to sine 2t minus 2 pi, which is also equal to sine 2 times the quantity t minus pi. Now, this one might make a little bit more sense to look at than this one here. Sine 2 times t minus pi. Pi is the shift here, right? Pi is also the same as the period. So if you're shifting by one period, you're going to stack right on top of itself. That's what this graph is showing, right? This graph is showing that it's stacked right on top. That's why you only see one graph. This green and red graph are stacked right on top of each other. Now, if I expand this, you'll typically will see this as sine 2t minus 2 pi. So 2 pi is the generic period, and because of that, that's why it falls out like this. Now, we can look at this one here, right? In blue, we're probably going to be told the function as sine 2t minus pi. But if we really want to know what the phase shift is, we want to distribute that omega term to sine 2 times quantity t minus pi over 2. So we would see this phase shift as pi over 2, as you can see here, right? So you can remember, how do we see the phase shift? We grab that point and move it back to the left, and you would see it stack right on top of each other. Here we have sine 2t minus pi over 2, or sine 2 times quantity t minus pi over 4. So a phase shift of pi over 4. So we'll see pi over 4 right here, and we can shift it back to the left. So you can see how omega is needed for phi, but typically when we look at a graph from raw data, you see it in this form. So if you see a non-unit, right, it's not 1 times t, right, something that's not that value, you want to distribute it so it looks like this. Or sorry, you want to factor it out so it looks like this, so you can identify what that phi term is on its own. All right, so the last thing we want to learn how to shift is the baseline, right? The baseline I define as where your 0 point is. So for sine of t, your baseline is 0, this part right here, right? So your general function sine of t plus 0 gives you your baseline of 0. Your amplitude we can measure as from the peak to the baseline. That's how we measure it. Sometimes folks will talk about from baseline, or sorry, from peak to trough divided by 2. So we can look at it from that perspective as well. That's the general definition when we look at something that's the baseline is non-zero. So in this case, sine t plus 2. So we're shifted up by 2. Here's your baseline. Sine t minus 2, shifted down by negative 2, right? Shift down by 2, right? So we're down at negative 2. So our amplitude is peak minus trough over 2. And so the amplitude is staying the same. It's still that coefficient in front of your sine term, right? So you can look at this one. Your peak is at 3. Your trough is at 1. So 3 minus 1 is 2. 2 divided by 2 is 1. In this case here, we have a peak at, what's this, negative 1. And a trough at negative 3. So negative 1 minus 3 is 2, divided by 2 is equal to 1, right? So, but if you can physically or graphically look at it, you know, it's probably easy enough to look at your peak and measure the distance from that to your baseline. So this is the last way we can manipulate our graph. So the next thing we're going to look at is, let's combine all these together. And I want to see if you can apply those concepts in drawing your own graphs. All right, so now we can throw all of these different control parameters together. We can control the amplitude, we control the frequency, we control the horizontal phase shift, we control the vertical shift by looking at the baseline. All of this can be combined together. So what I want you to do is get a graph, go from negative 4 to positive 4 for your amplitude, so you capture everything. Then go from 0 to 4 pi, so you have enough room to draw your graph. The first thing I want you to draw is 2 cycles of your sine t curve. Remember, it's going from positive 1 to negative 1 for your peak and trough range. And you have 1 cycle from 0 to 2 pi. So typically, the way you would graph it is you would find anytime you cross your baseline, you mark those points. And anytime you have a peak or trough, you mark those points. and then you connect the lines, right? So how closely you fit the in between points or in between line components, not that big a deal, right? But you want to make sure you hit the peak and trough and baseline points directly on. Okay, then look at these and think about what's changing for your amplitude, what's changing for your frequency, what's changing for phase shift, what's changing for your baseline. And I have a unit circle. I would draw that on the side if you want to check. It's a good way to check. I'm not going to walk through that process in this video, but we can do that in future videos too. So press pause, try to graph this. Use the sine t graph as a reference. I'm going to do that too. I'm going to walk through each of these relatively quickly so you can look at it. If you have any questions, go ahead and put in the comments. We're going to look at some functions, very basic form in this video, but we'll look at it in more depth in future videos too. All right, so hopefully you had a chance to try graphing these. I don't know how much you struggle with it, but if you have any questions, again, put it in the comments. So we'll walk through each of these individually. So let's take a look at the first, this blue graph function right here. So I know my baseline is shifted by -1. So we shift down here, -1. So this is my new baseline. The amplitude is equal to 2. So we stretch it out. So its amplitude is 2. We have a peak at +1 and a trough at -3, right? So that's going to give me an amplitude of 2. My frequency decrease, right? So I have omega of 1/2. So my period is going to go from 0 to 2 pi all the way to 0 to 4 pi now. And I have a phase shift, right? So if this is omega is 1/2, then my phase shift is going to be, let's see, 1/2 times t minus 2 pi. It's going to be phase shift of 2 pi. So if I grab this point and shift it back by 2 pi, that's going to be directly in line. Now, you don't compare that one to sine t, but I mean, the general concept is there. But if you want to do a direct comparison, like at the peak points, what you're going to want to do is compare it to the same frequency. So compare it to like a sine 1/2 t term. Okay. So hopefully you got at least some components of that one correct. Next, we have 1/2 sine t. I put plus or minus pi because for this one, it doesn't matter. It's half that period, so it's going to shift the same way, plus 3. So 1/2, right? We can see the amplitude is 1/2 as each of these vertical grid lengths is 1/2. Sine t, so the frequency is going to be the same as this one, the red line shown here. There's a shift of pi, right? So if I grab this point and I shift it this way or shift it this way, we'll get the same thing. And then a baseline shift of 3. So here's our baseline at 3. So that makes sense. Let's take a look at our next one. Our amplitude is increased to 4, which we show here. Baseline does not change. So the baseline is still at 0. There is no phase shift, no phi term, and our frequency is doubled, right? So omega is equal to 2, and we can see that because our period is equal to pi, right? So our period is cut in half. Lastly, we have sine of -t. We haven't played around with this one yet, but we say it's equal to sine t plus or minus pi. And so here we have sine t plus or minus pi. It's basically that phase shift. I'm not going to go in a lot of depth here for why sine of -t is the same. I want to just talk about the general concept here. So t is like our theta term, right? So this is our positive t. Then this would be our -t. So negative would be going in counterclockwise direction, right? This would be positive y. This would be our -y value. And the way to think about this one is kind of walk through the process. So sine -t is walking in the negative or the clockwise direction, where conventionally we walk in the counterclockwise direction. So we're going from a y value that's 0 along that positive x-axis to a negative value, -1 value, right, at the negative y-axis, to a 0 value again, and then to a positive 1 value, right? And what am I showing? I'm showing a pattern, right? And so you want to see at what location you will also see this pattern. Well, if you go in the counterclockwise direction, you would start at the negative x direction and go this way. You go from 0 to -1, -1 to 0, 0 to positive 1, and so forth. So this is 180 degrees. That's why that pi component is there. I know it's a little sloppy and messy here. We'll go more in depth in some of these trig functions in future videos, but I just want to show how the unit circle can help us visualize this effect. All right, let me erase this. The next thing I want to do is show you, so actually I want to throw all these graphs on top of each other, and so you can see how they stack and change here. So the next thing I want to do is look at what if I change it from sine to cosine. We have not gone in depth at all of looking at this. So I want you to give it a shot, right? Use the unit circle to help if you need it, and see if you can graph. Now again, I would suggest use sine and cosine as reference graphs to see that shift, right? So go ahead, press pause again, try on your own, and then come back when you're ready to walk through with me. Okay, so sine and cosine. We know because of the unit circle, sine is going to be the y values, cosine is going to be the x values. So there's some kind of repeating pattern. So I think we've talked in the previous video that there's just a phase shift. So let's see what that phase shift looks like. So sine's in red and cosine's in blue, right? So we start up here at 0, x is positive 1, y is 0. Then we slowly oscillate here, both are positive in this quadrant, and then we go to 90 degrees or pi over 2, then y is positive 1, x is 0, and so we see that shift right there. So what is this shift? Well, we're trying to find the point where we're here, and we can see the shift right in your cosine term, right? So if I write cosine t minus pi over 2, that's just this value shifted. So if I take this green graph and shift it over by pi over 2, I'm stacking right on top, right here, and shifting back pi over 2. If I go back, can I go back? Well, your red graph sine t is stacked right on top of cosine t minus pi over 2, right? So we can do the same thing that we do here by changing the amplitude, change the frequency, change the phase shift, and change the baseline for cosine as we did for sine. The starting point is different, but the effect is the same, right? Let's take a look at our next graph. 2 cosine t plus 2. So our baseline shifts by 2. Our amplitude is increased 2. So if I compare this graph to the blue graph, that's the direct comparison that I would like to make, right? The phase shift from sine is still there, right? So we have the same frequency, the shift is there. And then negative cosine t plus 2. Negative in front of cosine mirrors this blue graph across this x-axis, and then the plus 2 shifts it up by 2. So we're going to have to spend some more time in another video looking at the unique changes of putting negative signs within the function itself or outside for sine and cosine. They behave a little bit differently. So we'll have to look at that in a different video. Then there's a lot of examples that we can look at how oscillation shows up in engineering problems. But there's a lot here to digest. This function and the similar form of cosine, right? A cosine omega t minus v plus b are extremely powerful. You'll see them showing up in systems where you have multiple graphs and you want to compare them. Or if you have a certain data set in some kind of oscillation like this, and you want to adjust it or you want to modify it, and you need to figure out what physical systems can you use to control your amplitude, to control your frequency, to force a delay, phase shift delay, and then change a baseline. So there's a ton of different examples, and we'll walk through some of these in the future videos. and how effective you are in controlling these parameters through physical control systems really depends on your operation, right? Sometimes it's relatively easy, sometimes it's very difficult, and that's the fun in the engineering challenge. So we'll look at more of these in future videos too.